Hello Calc 3 and welcome back to the last video for chapter 13. We'll be talking about section 13.4 on curvature and normal vectors. So the goal for the video is to make rigorous the notion of how much a curve bends or turns at various points. And to give an idea of what I mean by that, you can look at the two examples of curves that I have drawn below. So if we look at the curve on the left, which is just a straight horizontal line, this is a curve that does not bend or turn very much. We would say that it does not have a lot of curvature, whereas the curve on the right turns a bunch of different times. It's bending all over the place. And we'd say that that curve has a lot of curvature. But how can we describe this idea more rigorously? If I gave you two curves and asked you to tell me which one had more curvature or which one seemed to curve more dramatically at different points, it would probably be pretty easy for you to figure out which one it was. But can we make this rigorous? Can we make it explicit? So let's begin by looking at what the unit tangent vectors look like at different points along the two curves from above. So with our constant curve on the left, the unit tangent vector is going to be the same regardless of which point we choose. So all of the unit tangent vectors are going in the same direction. Whereas if we look at the curve on the right here, the unit tangent vector is constantly changing and the direction is going all over the place. And so it seems like there's a correlation between the curvature or the dramatic curvature of a curve and the change of the unit tangent vector. And in fact, we're going to use the unit tangent vector to define the idea of curvature. So this leads to our first definition. If t is the unit tangent vector, which is a concept we talked about in section 13.3 of a smooth curve, then the curvature function of the curve is given by kappa is equal to the magnitude of the derivative of the unit tangent vector with respect to s, where remember s is the arc length parameter. Okay, so based on the definition here, if the magnitude of dt ds is large, then the curve is going to turn sharply at whatever point we're talking about. And if the magnitude of dt ds is small, then the curve turns slowly at that point. And if the magnitude of dt ds is equal to 0, then the curve is not going to have any turn or bend at that point, similar to the constant curve that we have up here on the left. Okay, but the definition that we just gave for kappa, or the curvature, was given with respect to the arc length parameter s, as opposed to the parameter t. So we want to figure out a way to talk about curvature with respect to the parameter t as opposed to s. So let's adapt our definition and come up with a new formula for curvature. So we know that kappa is by definition equal to the magnitude of the derivative of the unit tangent vector with respect to s. Using chain rule, we can write this as the derivative of the unit tangent vector with respect to t times the derivative of t with respect to s. And we can separate this magnitude into the magnitude of two different vectors. So we have the magnitude of dt ds and the magnitude of the derivative of the unit tangent vector with respect to t. And that'll give us 1 over the magnitude of ds dt times the magnitude of the derivative of the unit tangent vector with respect to t. And I think in the last video we said that ds dt, or the magnitude of ds dt, is equal to the magnitude of the velocity vector. And so we end up finding that if we have a smooth curve r of t, then the function for curvature can be calculated as 1 over the magnitude of the velocity function times the magnitude of the derivative of the unit tangent vector with respect to t, which is good because now we've taken the definition for curvature given with respect to s, the arc length parameter, and we've developed a formula for curvature that doesn't require us to use the arc length parameter. We can use t instead. So let's give a couple of different examples of finding the curvature of different curves. So we're going to start off with just a general equation for a straight line. So what we find out is going to be true for all straight lines. So we let r of t equal some constant vector c plus t times some other vector v. And this is the general equation for a line. And we want to find the curvature of our curve r. So to do so, we're first going to find r prime of t, and then we're going to find the magnitude of r prime of t. So r prime of t is going to equal the vector v, and the magnitude of r prime of t is going to equal the magnitude of v then, so that by definition, the unit tangent vector t is equal to the vector v divided by the magnitude of v. And this is a constant because the vector v is a constant vector. Now, by definition, or by the formula that we have listed above, kappa, or the curvature, will be equal to 1 divided by the magnitude of v times the magnitude of the derivative of t with respect to t. But because the unit tangent vector is constant, the derivative of the unit tangent vector with respect to t is just going to be 0. So we end up finding that kappa is equal to 0 for all t. So the curvature of any straight line is 0 at all points. And now for a second example, let's look at the general equation for a circle. So we let r of t equal a times cosine of ti plus a times sine of tj. So this is the equation for a circle of radius a. Although I guess it is centered at the origin, so maybe it's not as general as it could be. But if we have this curve r, then r prime of t in this case will equal negative a times sine of t I plus a times cosine tj, and we can take the magnitude of r prime of t as well. Ultimately, we use a trig identity, the fact that sine squared of t plus cosine squared of t is 1, to find that the magnitude of r prime of t is always equal to a, the radius of the circle. And then by definition, the unit tangent vector will be equal to v divided by the magnitude of v, which is equal to negative sine of ti plus cosine tj. Now we're going to take the derivative of the unit tangent vector with respect to t, and we find that that's equal to negative cosine of ti plus negative sine tj. And finally, the magnitude of dt dt is going to be equal to cosine squared of t plus sine squared of t, and take the square root of that. And again, cosine squared of t plus sine squared of t is equal to 1. So we find that the magnitude of the derivative of the unit tangent vector with respect to t is equal to 1. And for this reason, kappa, or the curvature, is equal to 1 divided by a times the absolute value of 1, which is of course just 1. So kappa is equal to 1 over a for all points along the curve. So we find that the curvature of the circle is going to be constant, it's going to be non-zero, and it's going to be equal to 1 divided by the radius of the circle for all points along the curve. Okay, so up until this point, we have been talking primarily about vectors that are tangent to the curve, but we can also talk about vectors that are orthogonal or perpendicular to the curve. We have a couple of different options for vectors that are orthogonal to the curve. So you can look in this diagram here, we have both the yellow and green vectors are orthogonal to the curve at these different points. But notice that the yellow vector is always pointing away from the direction in which the curve is turning, while the vector in green is pointing towards the direction in which the curve is turning. So we're going to denote the normal vector that is pointing in the direction of the curvature of the curve by a capital N. And we'll define it below here. So if we have a smooth curve in the plane and we're at a point where the curvature is not equal to 0, then the principal unit normal vector is given by n is equal to 1 divided by the curvature times the derivative of the unit tangent vector with respect to s, where again s is the arc length parameter. And just like before, working with the arc length parameter can be somewhat difficult, so we want to find a formula for calculating n with respect to t as opposed to the arc length parameter. Again, by definition, n is equal to 1 over kappa times the derivative of the unit tangent vector with respect to s. We can do a little bit more manipulation using chain rule, again, as usual, and then eventually canceling the dt ds with one another on the top and bottom of the fraction here, and finding that n is the same as the derivative of the unit tangent vector with respect to t divided by the magnitude of the derivative of the unit tangent vector with respect to t. And that will ultimately be our formula for calculating this vector n. So if we have a curve r and it has to be smooth, then the principal unit normal vector is given by, again, n is equal to the derivative of the unit tangent vector with respect to t divided by the magnitude of the unit tangent vector of the derivative of the unit tangent vector with respect to t. And let's give an example right away of calculating n. So if we have the curve r of t is equal to cosine of 2t I plus sine of 2t j, then let's find the vector n. To do so, we're going to need the unit tangent vector and then ultimately take the derivative of that. So the unit tangent vector is equal to the velocity vector divided by the magnitude of the velocity vector. And the velocity is just the derivative of r. So the velocity is equal to minus 2 sine of 2t I plus 2 cosine of 2t j. And the magnitude of the velocity vector is going to be the square root of each of the components of the velocity vector squared. Ultimately, we find that the magnitude is equal to 2 for all t, so that the unit tangent vector is going to be equal to minus sine of 2t I plus cosine 2t j. And now we can take the derivative of our unit tangent vector with respect to t, and we find that that's going to be equal to negative 2 times cosine of 2t I plus negative 2 times sine of 2t j. And lastly, the magnitude of the derivative of the unit tangent vector with respect to t is equal to 4 times cosine squared of 2t plus 4 times sine squared of 2t, where we're taking the square root of all of that, and we end up finding that is equal to 2, so that the principal unit normal vector is equal to negative cosine of 2t I plus negative sine of 2t j. So now we want to move into the idea of a circle of curvature for a curve in the plane at different points. And instead of starting with the definition, it's probably best to go down to the diagram that I have here, or the picture, explaining what's going on. We'll get an intuition and then go back up to the definition. So I have a curve drawn in the plane in red, and I've selected a particular point P in yellow along the curve. I've also drawn the unit tangent vector to the curve as well as the principal unit normal vector to the curve, both at the point P. And the circle in blue is what's going to be called the circle of curvature at the point P. And let's just notice some properties of this circle here. So first off, the circle is lying on the side of the curve such that the curve bends towards the circle as opposed to away. So I could have drawn the circle on this side of the curve down here, but now my curve would be curving away from my circle. And I don't want to do that. Also, this circle is tangent to the point P, so that it's touching the point P, but it's not touching the points that are very, very close to P on either side. And lastly, the circle has the same curvature as P. That's probably the most important property of this circle here, that it has the same curvature as P. And intuitively, this means that the circle kind of nestles in nicely to the curve there, so that it kind of approximates the curve along the circle for a little bit. Somewhat like approximating the curve with tangent lines from Calc 1, but here we have circles that are being used to approximate the curve. So with that being said, let's go back up to the definition of a circle of curvature. So again, we're assumed to have some plane curve, and we've specified some particular point on the plane curve P. Then the circle of curvature at P, where the curvature is not equal to 0 at P, is the circle in the plane of the curve with the following three properties. So the first is that it's tangent to the curve at P, which we saw before. 2, it has the same curvature as the curve at P. And then 3, it has a center that lies toward the inner side of the curve. So that last property is what I meant by the fact that the circle is lying on the side of the curve so that the curve is turning in towards the circle as opposed to turning away from the circle. Just a few more terms to go through. The radius of curvature of the curve at the point P is the radius of the circle of curvature. And the radius of the circle is going to be equal to 1 over kappa, and that'll be denoted rho. And the center of curvature of the curve at P is the center of the circle of curvature. So I actually have the vector n kind of pointing towards the center, which it always will, but the center of curvature would be this point here, right at the tip of n. Okay, so let's move on to an example where we're finding the circle of curvature. So let's say we have the function y equals x squared, which is graphed in the plane, and we want to find the circle of curvature of y equals x squared at the origin. The first thing to do is to parameterize y equals x squared so we can use all of the different formulas we've developed above. So to do that, we can let x equal t, and in that case, y is going to equal t squared. So we can write the curve given by y equals x squared as a vector valued function where the vector is given by r of t is equal to t I plus t squared j. And to find the circle of curvature, we're going to need the curvature at the origin so that we can find the radius of the circle. So we need kappa at the origin, and to get kappa, we're going to need the function for velocity. Velocity is the derivative of r. So v is equal to I plus 2t times j. And we're also going to need the magnitude of this velocity. So the magnitude of the velocity vector is equal to the square root of 1 plus 4t squared. And now we can write down a formula for our unit tangent vector, t. So t is going to equal I plus 2tj divided by the square root of 1 plus 4t squared. And we want to take the derivative of our unit tangent vector with respect to t. And ultimately, we find that the derivative is equal to this monstrosity of a formula right here. I don't want to go through taking that derivative. If you really want to, you can pause the video, take the derivative on a little piece of paper, and then just come back and make sure that you took the derivative correctly, but I don't want to go through it here. And we're going to evaluate the derivative of the unit tangent vector with respect to t at 0. So with respect to the I component, when we plug in 0, we get a -4 times a 0 times a bunch of other stuff, which doesn't matter because we've already multiplied by 0. So we get 0 in the I component. And for the j component, we get a 2 coming from this term here, and this term here is going to also be 0. So ultimately, the derivative of the unit tangent vector with respect to t evaluated at 0 is going to give us the vector 2j. And the magnitude of the velocity at 0 is going to be equal to 1. So to find that, you can just take 0 and plug it back into this equation right here, giving you the magnitude of the velocity. And at this point, we can finally figure out the curvature at 0. So the curvature is equal to 1 over the magnitude of the velocity at 0 times the magnitude of the derivative of the unit tangent vector with respect to t at 0. And this is ultimately going to be equal to 2. So the curvature at the origin is equal to 2. And because of that, the radius of curvature is going to be equal to 1/2. So the radius of our circle of curvature is equal to 1/2. And at t equals 0, we have that the unit tangent vector is equal to I. Let me just draw the parabola here. So it's going to look something like this, just so that this makes a little more sense. So again, the unit tangent vector at 0 is going to be equal I, so it's going to point in the x direction out here, and the principal unit normal vector is going to be j. It's going to point directly up along the y-axis. So we know that the principal unit normal vector is going to point towards the center of the circle of curvature, and we also know that the circle has radius 1/2, and because of these two facts, we can conclude that the center of the circle of curvature is going to be at the point 0, 1/2. So it's going to look something like this, assuming that that normal vector points to the center, all the way to the center there. So the equation for the circle is going to be given by x minus 0 squared plus y minus 1/2 squared is equal to 1/2 squared. And we've calculated our circle of curvature here. Okay, so finally let's move on to the last subsection of section 13.4. And consequently the last subsection of chapter 13. And the idea of this last subsection is just to talk about how all of the terms and definitions and formulas that we've given above generalize to space curves. So the curves that we've been talking about through the preceding material for section 13.4 have been curves in the plane, but that was just to simplify the pictures that I had to draw and possibly make it easier to develop the intuition right off the bat. But all of these definitions are just going to generalize to curves in higher dimensions. So the only thing we have to do for this section is give an example where we're using some of the terms for a curve in space, because all of the things just generalize pretty directly. So let's say that we want to find the curvature for an arbitrary helix. That's our goal. And the function for the arbitrary helix is given by r of t is equal to a cosine ti plus a sine tj plus btk, where a and b are just some constants. and we want to find the formula for the curvature of this curve. We're going to start off by finding the function for velocity. So the velocity is going to be the derivative of r, and we find that the velocity is equal to negative a sine ti plus a cosine tj plus bk, and the magnitude of the velocity is equal to a squared sine squared t plus a squared cosine squared t plus b squared, and the square root of all of that. And using the fact that sine squared t plus cosine squared t is equal to 1, we find that ultimately the magnitude of the velocity is equal to the square root of a squared plus b squared for all t. So notice that the magnitude of the velocity is going to be constant, depending only on which constants a and b we choose for our helix. So once we have this information, we can calculate the unit tangent vector, which is equal to the velocity vector divided by the magnitude of the velocity. So that gives us a scalar 1 divided by the square root of a squared plus b squared, multiplying the velocity vector, which again is negative a sine ti plus a cosine tj plus bk. And now we can start to write down what the curvature is. So kappa is going to be equal to 1 divided by the magnitude of the velocity, which we've already said is equal to the square root of a squared plus b squared, multiplied by the magnitude of the derivative of the unit tangent vector with respect to t. So let's take the derivative of the unit tangent vector with respect to t. So 1 over the square root of a squared plus b squared is a constant, so we can just keep it the same out here. And now we'll take the derivative of the vector, the velocity vector, and we get negative a times cosine ti plus negative a times sine tj, and notice that this bk term is going to go to 0 because the derivative of the constant b is going to be equal to 0. And if we take, we can split up this magnitude, the magnitude of the derivative of the unit tangent vector with respect to t. We can split that into the magnitude of 1 divided by the square root of a squared plus b squared times the magnitude of a times the magnitude of cosine ti plus sine tj. And ultimately, simplifying a little bit, that will give us this a divided by a squared plus b squared times the magnitude of cosine ti plus sine tj. But the magnitude of cosine ti plus sine tj is equal to 1, because again, cosine squared of t plus sine squared of t is equal to 1. And so ultimately, we find that the curvature of our arbitrary helix is equal to a divided by a squared plus b squared. So at all points on the helix, the curvature is completely determined by our choice of the constants a and b. But the curvature is going to be constant throughout the entire helix. Also, if we let b equal 0, then we find that the curvature is going to be equal to 1 over a, which is expected because if b is equal to 0, then our original curve just becomes the arbitrary equation for a circle. And we've already said that the curvature of a circle is going to be equal to 1 divided by a, where a is the radius of the circle. Okay, so that is the end of the material for section 13.4, as well as the end of the material for all of chapter 13, and the end of the material that will be covered on the first exam. So I think the next video is just going to be me doing a few different problems related to chapter 12 and 13 in preparation for the exam that I should be sending out to you soon.